Hey there, tonight we're embarking on a journey into the sky itself, a quiet exploration of how our world's weather truly works. It's a story of unseen forces and gentle transformations, perfect for unwinding. Before we drift into the atmospheric wonders, take a moment to settle in. If you're enjoying this calm journey, consider giving us a like and subscribing. It helps us continue these explorations together. Our story begins not with a grand storm, but with something far more subtle, the soft hum of morning fog. Imagine a world waking up, shrouded in a veil of mystery where familiar shapes become whispers. For centuries, this everyday phenomenon sparked deep wonder. How did the air, so clear moments before, suddenly thicken into a damp, swirling embrace? It felt like magic, a breath from an unseen world. Early observers, philosophers, and storytellers tried to make sense of it. Sometimes, the mist was thought to be the breath of sleeping giants or spirits moving between realms, cloaking the earth. These were comforting tales, but the human mind yearned for more concrete answers. The scientific journey into weather began with simple questions. What asterisk is asterisk this mist, and where does it truly come from? The invisible components of air became a focus. Could air hold water? If so, how much, and what made it release its watery grip to become visible fog or dew? These were profound puzzles. In the 17th century, a shift began. No longer content with speculation, curious minds sought to measure. How could one quantify something as elusive as the dampness in the air? The earliest instruments were ingenious in their simplicity. A strand of human hair, known to lengthen with moisture, could be used to indicate changes in humidity, a humble beginning. These early hygrometers, though imprecise, marked a crucial step. They transformed qualitative observation into quantitative data, however crude. The atmosphere was becoming measurable. By the 18th century, instruments grew more refined. The psychrometer emerged, using two thermometers, one dry, one wet, to calculate relative humidity. It offered greater accuracy. Scientists meticulously recorded readings day after day, season after season. They sought patterns, trying to understand the invisible dance between temperature, air, and water vapor. This painstaking work laid the foundation for deeper insights. It revealed that the air's capacity to hold water was not constant, it changed with temperature. The early 19th century brought John Dalton, a quiet, observant chemist. His work on gases would profoundly shape our understanding of atmospheric moisture. Dalton theorized that each gas in a mixture, including water vapor, behaved independently. This was a radical idea, simplifying the complex atmospheric soup. He proposed that air could only hold a certain amount of water vapor at a given temperature before it became saturated. Beyond that point, the vapor would condense. This concept of saturation was key. It explained why a warm, humid day might feel stifling, yet a cold, damp day could bring dense fog, even with less total water in the air. Dalton's experiments often involved enclosed spaces, carefully controlling temperature and pressure to observe the behavior of water vapor. His patience was legendary. He noticed that if he cooled the air in his apparatus, condensation would appear. The temperature at which this happened was crucial. It was the dew point. The dew point became a measurable threshold. Below this temperature, water vapor would transform into liquid, forming dew on grass or, if suspended in air, fog. This discovery elegantly linked temperature, humidity, and the visible manifestation of water. Fog was no longer a mystery, but a predictable outcome of atmospheric conditions. Yet a subtle question lingered. Even when air reached its dew point, fog didn't always form instantly. What was the catalyst? What helped the tiny water droplets appear? Scientists began to suspect that something else was needed, something microscopic. Pure, clean air, when cooled, resisted forming fog, even at its dew point. This led to investigations into condensation nuclei, tiny particles suspended in the air. Dust, pollen, salt crystals, even pollution could serve as seeds for water droplets. A Scottish physicist, C.T.R. Wilson, famously demonstrated this with his cloud chamber in the late 19th century. He showed that without these particles, supersaturated air remained clear. In his chamber, when dust-free air was cooled below its dew point, nothing happened. But introduce a tiny puff of smoke, and suddenly a miniature cloud would bloom. These microscopic particles provided the surface area, the tiny foothold, for water vapor molecules to cling to and begin their transformation into liquid droplets. So morning fog, that gentle atmospheric whisper, is a symphony of conditions: cooling air, sufficient water vapor reaching the dew point, and the presence of these unseen nuclei. It's a testament to centuries of patient observation and careful experimentation, transforming ancient wonder into scientific understanding, one subtle discovery at a time. The fog is not just water, it's a visible story of temperature, pressure, and the countless tiny particles that drift silently around us, playing their part in the weather's grand design. This quiet understanding of fog, from ancient mystery to scientific clarity, is just the beginning of our journey. The atmosphere holds many more secrets. Next, we'll lift our gaze higher, beyond the morning mist, to where the graceful dance of winds aloft shapes our world in ways we often don't perceive. Consider the invisible currents, the rivers of air that flow silently thousands of feet above us, carrying weather systems across continents. These are not just random breezes, they are organized, powerful forces driven by the sun's energy and the Earth's rotation, orchestrating global weather. Understanding these winds requires a different kind of observation, looking not at static conditions, but at dynamic, ever-changing movements on a grand scale. From the ground, we might feel a gentle breeze, but high above, powerful jet streams can propel aircraft and shape our forecasts, unseen by the naked eye. The story of these winds is one of immense energy, subtle balances, and the constant interplay of forces that govern our planet's climate. It's a reminder that even the most fleeting atmospheric phenomena are part of a vast, interconnected system, each piece contributing to the whole. As we conclude our first chapter, let the quiet complexity of morning fog settle in your mind, a testament to nature's subtle artistry and human perseverance. We'll soon delve deeper into these atmospheric whispers, uncovering more of the science that dances above our heads, even as the world sleeps. The morning fog, a visible breath, had revealed the subtle dance of water and air. But above the mist, another, grander ballet unfolded, an invisible choreography of currents. For millennia, humanity looked up not just at stars but at the moving air. Ancient mariners, relying on instinct and observation, charted their courses by the steady push of the winds. These winds were more than breezes, they were highways across oceans, shaping early migrations and forging trade routes between distant lands. Their patterns were crucial for survival. Yet the *Y* remained a mystery. Why did winds consistently blow from certain directions? What invisible hand guided their persistent flow across the globe? Early thinkers often attributed wind to divine breath or elemental forces, but the scientific mind yearned for mechanical explanations, for laws governing the atmosphere. The 17th century brought a new rigor. Galileo Galilei, with his meticulous experiments, began to challenge long-held assumptions about the very nature of air. He demonstrated that air, though unseen, was not weightless. It had substance, exerting a measurable pressure, a concept that fundamentally altered atmospheric understanding. This was a profound shift. If air had weight, then differences in its distribution could create forces. The invisible atmosphere was now understood as a tangible entity. The ability to measure this pressure systematically became paramount. How could one quantify the invisible push of the air around us? Evangelista Torricelli, a student of Galileo, sought an answer. In 1643, his invention offered a breakthrough: the barometer, a column of mercury balanced against atmospheric weight. The barometer provided the first systematic means to measure atmospheric pressure. Scientists could now track its fluctuations, revealing a direct link to weather changes. Daily readings began to reveal patterns. High pressure often meant clear skies, low pressure heralded storms. The invisible hand of pressure was becoming visible through data. It became clear that air flowed from areas of high pressure to areas of low pressure. This fundamental principle explained the very genesis of wind. With this understanding, a larger question emerged. What drove these global pressure differences? How was the atmosphere heated and cooled on a planetary scale? In the 18th century, George Hadley proposed a revolutionary model. He linked the sun's intense heating at the equator to large-scale atmospheric circulation. Hadley envisioned air rising over the warm tropics, flowing poleward, cooling, and then sinking back towards the surface. This explained the persistent trade winds. These Hadley cells offered an elegant, if simplified, explanation for global wind patterns, especially those reliable breezes that filled the sails of exploration ships. Yet actual observations showed more complexity. Winds didn't always blow directly north or south. Something else was at play, subtly deflecting their paths. The Earth's rotation was the key. As our planet spun, it imparted a powerful, yet unseen, influence on anything moving freely across its surface, including air. In the 19th century, William Ferrel elucidated this effect. He showed how the Coriolis force, an apparent deflection, curved winds to the right in the northern hemisphere and left in the southern. This invisible force was crucial. It explained why hurricanes spun counterclockwise and why large-scale weather systems drifted as they did. The Coriolis effect transformed our understanding of global circulation, adding layers of intricate detail to Hadley's foundational model. The atmosphere was far from simple. Even with these advancements, much remained unseen, especially in the higher reaches of the atmosphere. The world above 20,000 feet was largely unknown territory. It took the urgency of World War II to reveal one of the atmosphere's most dramatic secrets: the jet stream. Pilots on long-range bombing missions reported encountering incredibly strong head or tailwinds at high altitudes, far more powerful than anything previously anticipated. These weren't mere gusts, they were persistent, narrow bands of extremely fast-moving air, veritable rivers flowing across continents, thousands of feet up. The serendipitous discovery of jet streams fundamentally altered meteorological understanding. They were powerful orchestrators of global weather. These high-altitude currents transported weather systems with incredible speed, influencing everything from storm paths to temperature extremes on the ground. Mapping and understanding these invisible highways of the sky became a new frontier in atmospheric science, crucial for both aviation and forecasting. The graceful dance of winds aloft, from the ancient trade winds to the roaring jet streams, is a testament to the Earth's dynamic energy and ceaseless motion. We've journeyed from the subtle hum of fog to the powerful currents that shape our planet's climate, each discovery built upon the last, revealing deeper complexities. The atmosphere, once a realm of mystery, slowly yielded its secrets through patient observation and ingenious experimentation. From Galileo's simple weight experiments to Ferrel's complex equations, the human quest for understanding continued, driven by an insatiable curiosity. The air around us is not merely empty space. It's a vast, intricate system, constantly in motion, carrying energy and moisture across vast distances. These invisible currents are the architects of our weather, shaping the conditions that bring warmth, cold, and critically, precipitation. The winds don't just move air, they carry the very ingredients for clouds and rain, transporting moisture from oceans to continents. This transport mechanism is fundamental. Without these atmospheric rivers, many parts of our world would be barren, devoid of life-giving water. The journey of a single water molecule from ocean surface to mountain rain is guided by these global wind patterns, a silent, continuous cycle. As we drift now from the winds that guide the sky, we prepare to witness the next transformation, how these airborne travelers coalesce into visible form. Next, we will explore the delicate alchemy of cloud formation and the gentle descent of rain, discovering how the unseen becomes the life-giving visible. The winds, those unseen currents we just explored, carried moisture across vast distances. But how did this invisible vapor transform into the majestic, tangible forms we call clouds? It was a question that long captivated observers. For millennia, clouds were seen as omens or ethereal landscapes. Their ever-changing forms seemed to defy simple explanation, a canvas painted anew each day. Yet the scientific mind seeks order. In the early 19th century, Luke Howard, a quiet English chemist, began to observe clouds not as fleeting spirits but as definable structures. Howard meticulously recorded their shapes, altitudes, and behaviors from his London home for years, seeking patterns in their fleeting beauty. His work led to a revolutionary classification system, giving us the names we still use: cumulus, stratus, cirrus, nimbus. He brought scientific language to the sky. This naming allowed scientists worldwide to communicate precisely about atmospheric phenomena. It created a shared vocabulary for the sky. With clouds now definable, the next step was understanding their place within Earth's water. They were not isolated events, but part of a continuous journey. The 19th century solidified the water cycle, water moving from oceans to atmosphere to land and back. Clouds were the visible atmospheric stage. We knew vapor rises invisibly. Now we understood how that vapor, carried by winds, would eventually cool and condense into visible cloud droplets. But what caused air to cool enough for vast cloud formation, not just ground fog? The answer often lay in atmospheric uplift. As warm, moist air rises, it expands due to lower pressure. This expansion causes it to cool, similar to a gas released from a canister. Once this rising, cooling air reaches its dew point, water vapor condenses onto microscopic particles, forming the tiny liquid droplets or ice crystals of clouds. Just as with fog, these condensation nuclei were essential. Without them, even supersaturated air struggles to form droplets, remaining clear. C.T.R. Wilson, whose cloud chamber showed fog formation, also used his ingenious apparatus to demonstrate cloud formation principles with striking clarity. In his chamber, Wilson precisely controlled temperature and pressure, mimicking atmospheric conditions found high above, scaled down to a laboratory flask. By rapidly expanding moist air, he mimicked uplift. In the presence of nuclei, tiny cloud wisps would instantly appear, a miniature cloud. This allowed direct observation, vapor transforming into droplets. It was a microcosm of the vast cloud formations above our heads. But forming a cloud was one thing, making it rain was another. Cloud droplets are incredibly tiny, too small to fall to Earth. A typical cloud droplet is only about 20 micrometers across, so light that air currents easily keep it aloft. For rain, it needs to be 100 times larger. How did these minuscule droplets grow heavy enough to overcome air resistance and fall as precipitation? This question puzzled meteorologists for decades. Eventually, two primary mechanisms explained how clouds shed moisture: the Bergeron-Feindeisen process and the collision coalescence theory. The Bergeron-Feindeisen process, early 20th century, explained rain formation in cold clouds, often at higher altitudes or in temperate zones. It begins with supercooled water. Liquid water droplets can exist at temperatures far below freezing, sometimes as low as -40 degrees Celsius. Crucially, ice crystals have lower saturation vapor pressure than supercooled water droplets. Ice attracts water vapor more readily. So, in a mixed cloud, water vapor preferentially evaporates from liquid droplets and deposits onto the ice crystals, making them grow. The ice crystals rapidly grow, becoming large enough to fall. Descending through warmer cloud parts, they collide with other supercooled droplets, freezing. If these growing ice crystals fall through air above freezing, they melt, becoming raindrops. Much of our rain starts this way. For warmer clouds, common in the tropics, collision coalescence dominates. Here, liquid droplets grow by simply bumping into each other. Larger droplets fall faster, sweeping up smaller droplets in their path. With each collision, they grow larger, gaining momentum. Eventually, they become heavy enough that air resistance can no longer support them. They descend as raindrops, overcoming terminal velocity. These two processes explain the vast majority of precipitation, from gentle drizzles to torrential downpours, across our planet. So the sky's canvas, adorned with Howard's cumulus and cirrus, is a dynamic stage where water vapor transforms and returns to Earth. This continuous cycle of cloud formation and gentle rain is fundamental to life, replenishing rivers and nourishing plants. From patient observations of cloud shapes to intricate laboratory experiments and complex theoretical models, our understanding grew in layers. It was a testament to human curiosity, the drive to unravel profound mysteries of our natural world, one droplet at a time. The gentle patter of rain, often a source of calm, is a culmination of these intricate atmospheric dances, a quiet miracle unfolding. But not all rain is gentle. Sometimes the sky's tears are accompanied by a far more dramatic display of power. These powerful storms, while terrifying, also reveal the immense energy stored within the atmosphere, waiting to be unleashed. As we leave the quiet beauty of cloud formation and gentle rain, we prepare to witness the atmosphere's more intense expressions. Next, we will venture into the heart of these thunderous charges, uncovering the secrets behind lightning, thunder, and storms. The winds, those great architects of our atmosphere, carried moisture and shaped clouds into gentle rain. But sometimes, the sky's canvas gives way to a far more dramatic display of power, a thunderous charge that commands attention. Lightning, a sudden, blinding flash followed by the deep rumble of thunder, has always been one of nature's most awe-inspiring and terrifying phenomena. For millennia, it was seen as a sign of divine power, a force beyond human comprehension. Ancient cultures wove elaborate myths around these sky-splitting events, attributing them to gods wielding celestial hammers or fiery spears. The raw energy of a storm seemed to defy any earthly explanation. But as the Age of Enlightenment dawned in the 18th century, a new spirit of inquiry began to question these supernatural explanations. Minds sought natural laws even for the most formidable forces of the sky. Among these curious minds was Benjamin Franklin, a polymath whose interests ranged from politics to the very nature of electricity. He observed the sparks and shocks of early electrical experiments and saw a profound connection. Franklin hypothesized that lightning was not a divine weapon, but simply a massive electrical discharge, a phenomenon that could be studied and understood by human reason. This idea was radical, to suggest that the terrifying power of a thunderstorm was merely a larger version of the static electricity one could generate in a laboratory was a bold challenge to prevailing beliefs. To prove his hypothesis, Franklin devised a daring and now legendary experiment in 1752. He planned to draw electricity from a thundercloud using a simple kite. On a stormy day, he flew his kite with a metal key attached to the wet string. A Leyden jar, an early capacitor, was connected to collect any charge. As the storm passed overhead, he touched the key and a spark jumped to his finger. It was a fleeting, dangerous moment of confirmation. Lightning was indeed electricity. Franklin's experiment was a pivotal breakthrough, demystifying one of nature's most formidable forces. The sky's electric drama was now brought into the realm of scientific inquiry. But Franklin's discovery, while revolutionary, opened a new, profound question. How did these vast electrical charges actually form within the clouds themselves? The challenge was immense, understanding the intricate process of charge separation in a turbulent, opaque environment thousands of feet above the ground. Early scientists pondered the dynamics of ice crystals, water droplets, and air currents, seeking the microscopic origins of such macroscopic power. Hypotheses emerged, often involving friction, the continuous rubbing together of particles within the tumultuous storm cloud. In cold clouds, where temperatures are below freezing, a complex dance occurs between ice crystals and supercooled water droplets, which remain liquid below freezing point. As these particles collide, especially larger graupel soft hail with smaller ice crystals, charges are exchanged. The exact mechanisms are still debated, but the outcome is clear. Typically, the heavier, negatively charged particles fall towards the base of the cloud, while lighter, positively charged particles are carried upwards by strong updrafts. This separation of charges creates an immense electrical potential within the cloud, a vast voltage difference between the top and bottom and between the cloud and the ground. The cloud effectively becomes a giant capacitor, storing vast amounts of electrical energy, building to a critical point where the air can no longer insulate the charge. Despite these theoretical advancements, the internal workings of storms remained largely hidden, their turbulent cores inaccessible to direct human observation. Models and hypotheses were useful, but scientists yearned for a way to see inside the storm, to track its movements and understand its structure in real time. The breakthrough came not from meteorology, but from the urgency of World War II, with the rapid development of radar technology for military defense. Initially designed to detect enemy aircraft, radar operators soon noticed strange, persistent noise on their screens that wasn't planes. These mysterious echoes were, in fact, reflections from rain, snow, and other precipitation, an accidental discovery that would revolutionize weather science. After the war, scientists quickly adapted this military technology for meteorological purposes, building dedicated weather radar systems. These new instruments sent out radio waves that bounced off raindrops, hail, and snow, returning echoes that could be translated into visual maps of precipitation. For the first time, meteorologists could visualize storm structure, track its movement, and even estimate its intensity in real time. This was a revolutionary leap, transforming weather forecasting from educated guesswork into a data-driven science. The storm's heart was finally visible. Radar provided the form of the storm, but the question remained: what powered such immense fury? What was the engine driving these colossal atmospheric events? The answer lay in the atmosphere's fundamental processes, particularly in the rapid ascent of warm, moist air, a phenomenon known as convection. As this air rises, it cools, and the water vapor within it condenses into liquid cloud droplets. This phase change from gas to liquid releases an enormous amount of energy. This released energy is called latent heat. It's the same heat that was absorbed when the water evaporated from the Earth's surface. The latent heat released during condensation warms the surrounding air, making it even more buoyant and causing it to rise faster. This creates a powerful positive feedback loop. Rising air condenses, releases heat, which fuels more rising air, intensifying the updraft. A thunderstorm, therefore, is a colossal heat engine, efficiently converting the latent heat of water vapor into the kinetic energy of powerful updrafts, downdrafts, and ultimately, severe weather. This understanding allowed meteorologists to define the distinct stages of a thunderstorm's life cycle, from its birth to its eventual dissipation. The initial cumulus stage is characterized by solely updrafts, as warm, moist air rises and builds the cloud vertically, a quiet beginning. The mature stage sees both strong updrafts and downdrafts, heavy rain, lightning, and thunder. This is the period of the storm's greatest intensity. Finally, the dissipating stage occurs as downdrafts dominate, cutting off the supply of warm, moist air, causing the storm to weaken and fade, leaving behind a quieter sky, perhaps hinting at a different kind of atmospheric wonder to come. The thunderous charge of storms, which had once filled the sky with electric drama, eventually gives way. As the powerful updrafts weaken and the latent heat dissipates, a quieter calm descends upon the atmosphere. But a quieter sky does not mean an empty one. As temperatures drop and the air chills, a different kind of atmospheric wonder can emerge, a delicate transformation known as falling snow. For centuries, the intricate beauty of snowflakes captivated curious minds. How could something so ephemeral, so seemingly random, possess such precise, often six-sided symmetry? One of the earliest recorded scientific ponderings came from Johannes Kepler, the astronomer, in 1611. He noticed the consistent hexagonal shape of snowflakes and found himself deeply intrigued. Kepler penned a short treatise, Strena su de nive sexangula, a New Year's gift, or on the six-cornered snowflake. It was a philosophical and scientific inquiry into this peculiar natural form. He observed that while all snowflakes were six-sided, no two seemed identical in their detailed patterns. This paradox fueled his curiosity: uniformity in basic structure, infinite variety in complexity. Kepler speculated on the underlying geometric principles, linking the hexagonal form to the most efficient packing of spheres. His insights were remarkably ahead of their time, hinting at molecular arrangements. A few decades later, in the 17th century, the French philosopher René Descartes also turned his attention to these frozen marvels. He made some of the earliest detailed illustrations of snowflake forms. Descartes noted not just the common six-pointed stars, but also needle-like crystals and small hexagonal plates. His work expanded the known diversity of snow crystal habits. These early observations, though limited by the technology of the time, marked crucial steps. They transformed snow from a mere weather phenomenon into an object of serious scientific investigation. Yet the true, astonishing diversity and intricate detail of individual snowflakes remained largely hidden. too small and too fleeting for the naked eye or simple drawings to fully capture. The challenge was immense: how to preserve and study something so delicate which melted away almost instantly. A new approach and a new technology would be needed. This challenge was taken up by a quiet, self-taught farmer in Vermont in the late 19th century, Wilson "Snowflake" Bentley. Bentley was utterly captivated by the beauty of individual snow crystals. He was determined to capture their fleeting forms for study, a lifelong passion. He spent years perfecting a technique to photograph individual snowflakes, adapting a microscope to a bellows camera, often working in unheated sheds in freezing temperatures. His painstaking efforts yielded thousands of microphotographs, each a testament to his patience and ingenuity. He revealed a hidden world of astonishing complexity and artistry. Bentley's work popularized the idea that no two snowflakes are alike, a phrase that captured the wonder of nature's individual creations. But beyond the aesthetic wonder, Bentley's photographs posed a profound scientific question. What precise factors led to such an immense variety of shapes, all based on a six-fold symmetry? The answer lay in the subtle yet powerful interplay of temperature and humidity within the cloud where the ice crystal formed and grew. A snowflake begins as a tiny dust particle or pollen grain, a condensation nucleus high in the atmosphere, where water vapor condenses directly into ice. As this nascent ice crystal falls through the cloud, water vapor molecules deposit onto its surface. The rate and manner of this deposition are exquisitely sensitive to its environment. Even slight changes in temperature and humidity as the crystal descends can drastically alter its growth pattern, leading to different forms. Scientists have mapped these relationships, creating ice crystal growth diagrams that show how specific temperature and humidity ranges produce distinct snowflake shapes. For example, between -2 and -8 degrees Celsius, ice crystals tend to grow into columns or needles. In contrast, between -10 and -20 degrees Celsius, plates and stellar dendrites are common. The intricate, feathery dendrite snowflakes, often depicted, form in a narrow range of colder temperatures and high humidity, where water vapor is abundant. As a crystal falls through varying layers of temperature and humidity within a cloud, its growth pattern changes. One arm might encounter slightly different conditions than another. This continuous, dynamic interaction with its environment is what gives each snowflake its unique, complex structure, a microscopic record of its journey through the sky. The underlying six-fold symmetry, however, remains constant. This is due to the hexagonal arrangement of water molecules when they freeze into a crystal lattice, a fundamental property of ice. So the whisper of falling snow is a testament to the precise dance of physics and chemistry, each crystal a tiny, frozen masterpiece reflecting its atmospheric journey. But not all frozen precipitation takes the form of delicate snowflakes. Other atmospheric conditions can lead to very different outcomes. Consider sleet, also known as ice pellets. These are raindrops that freeze before they hit the ground, typically falling as small, hard, translucent spheres. Sleet forms when there is a layer of freezing air near the surface, but a warmer layer of air exists above it. Rain falls through the warm layer, then freezes in the cold layer. Freezing rain, another form, is liquid rain that falls through a sub-freezing layer of air but freezes on contact with surfaces that are at or below 0 degrees Celsius. This occurs when the freezing layer near the ground is deep enough to cool the raindrops to below freezing, but not deep enough for them to completely freeze solid before impact. Then there is hail, a much more formidable form of ice. Unlike snow or sleet, hail typically forms within the powerful updrafts of intense thunderstorms. Hailstones grow as ice pellets are repeatedly carried upwards by strong currents, accumulating layers of supercooled water that freeze upon impact, much like an onion. Each cycle through the cloud's different temperature zones adds another layer of ice until the hailstone becomes too heavy for the updrafts to support and it falls. From the delicate, intricate snowflake to the destructive power of hail, each form of frozen precipitation is a direct consequence of precise atmospheric conditions and the journey of water through the sky. This understanding, built on centuries of observation, ingenuity, and scientific inquiry, allows us to appreciate the subtle artistry and powerful mechanics of our planet's atmosphere. As we reflect on the whisper of falling snow and the many forms of ice, we are reminded of the interconnectedness of all atmospheric phenomena, preparing us for a final reflection on the grand design of global weather itself. The whisper of falling snow had shown us nature's intricate crystallization, a quiet testament to atmospheric precision. But as the mid-20th century dawned, a new ambition stirred, to not just observe weather, but to predict its grand, interconnected symphony with unprecedented accuracy. Forecasting had long been an art, a blend of observation, experience, and intuition. Meteorologists painstakingly charted data, drawing lines on maps to predict the next day's winds and rains. It was skilled work, but inherently limited by human processing power. The atmosphere, however, was a system of immense complexity, governed by countless interacting variables. To truly understand its future, one needed to solve a vast set of mathematical equations, far beyond the scope of manual calculation. The vision of numerical weather prediction, using mathematics to model the atmosphere, had existed for decades. But the tools to realize it were only just emerging. The first electronic computers, massive machines humming with vacuum tubes. In the 1950s, pioneering scientists like John von Neumann and Jules Charny began to harness these nascent computing behemoths. Their goal, to simulate the atmosphere's future, one calculated step at a time. The initial forecasts were crude, taking hours to compute a single day's prediction. Yet they were a profound breakthrough, a proof of concept that the atmosphere's secrets could be unlocked through computation. This marked a fundamental shift, transforming meteorology from a largely empirical science into one increasingly driven by physics and mathematics. The atmosphere was becoming a system that could be modeled. Despite these advances, a significant challenge remained: gathering enough real-time data from across the globe. Vast stretches of oceans and uninhabited lands remained blind spots, limiting the model's accuracy. The solution, literally, was to rise above the Earth. If we couldn't place sensors everywhere on the surface, perhaps an eye in the sky could provide the missing pieces. The dawn of the space age brought this possibility to life. In 1960, the United States launched TIROS-1, the television infrared observation satellite, the world's first successful weather satellite. TIROS-1, though primitive by today's standards, sent back grainy black-and-white images of cloud patterns, revealing global weather systems in a way never before possible. For the first time, meteorologists could see the swirling arms of hurricanes forming over the open ocean, track the movement of frontal systems across continents. The entire planet's weather was becoming visible. This marked an unprecedented leap in observation. Satellites provided a continuous global snapshot, feeding vital data into the ever-improving numerical models. Over the decades, satellite technology advanced rapidly. From simple visible light cameras, they evolved to include infrared, microwave, and specialized sensors, peering through clouds and measuring atmospheric temperature and moisture profiles. This constant stream of data from space, combined with ground-based observations and supercomputing power, began to reveal the truly interconnected nature of Earth's atmospheric systems. No longer was weather seen as a series of isolated regional events. It was a single, planetary symphony where a flutter in one part of the world could resonate profoundly in another. One of the most profound realizations of this interconnectedness came with the study of phenomena like El Niño and La Niña, oceanic events with far-reaching atmospheric consequences. El Niño, a warming of Pacific Ocean waters, was once thought to be a localized event, but data from satellites and ocean buoys revealed its global teleconnections. Changes in Pacific sea surface temperatures could alter atmospheric pressure patterns, shifting jet streams and influencing rainfall thousands of miles away, from droughts in Australia to floods in Peru. La Niña, its cooler counterpart, brought its own distinct set of global impacts, a testament to the ocean's profound influence on atmospheric circulation. This understanding of ocean-atmosphere coupling transformed our view of climate. The ocean was not merely a passive recipient of weather, but an active, powerful driver of long-term patterns. The discovery of these global connections highlighted the Earth system as a single, dynamic entity, where every component, oceans, land, ice, and atmosphere, was inextricably linked. This realization fueled the development of increasingly sophisticated climate models, designed not just for short-term forecasts, but to understand the long-term evolution of our planet's weather. These models, running on the most powerful supercomputers, could simulate decades, even centuries, of atmospheric behavior, offering glimpses into our climatic future. As these models grew more powerful, a new, critical question emerged. What was the human impact on this delicate balance? Was our presence altering the very symphony of our weather world? Early concerns about atmospheric pollution had existed, but now, with global data and sophisticated models, the scale of human influence became undeniably clear. The burning of fossil fuels, deforestation, and industrial processes were releasing greenhouse gases, trapping heat, and subtly, but profoundly altering the Earth's energy budget. Climate models began to project future scenarios, suggesting changes in global temperatures, sea levels, and the frequency of extreme weather events. This was no longer just about forecasting tomorrow's rain. It was about understanding the long-term destiny of our planet's atmosphere, a responsibility that weighed heavily on the scientific community. The quest for understanding the atmosphere's delicate balance continues, driven by an unwavering curiosity and a growing urgency. Prediction accuracy is constantly improving, but the system remains vast and complex. Every new satellite, every more powerful computer, every refined algorithm brings us closer to unraveling the intricate dance of winds, clouds, and storms. From the soft hum of morning fog to the thunderous charge of storms, from the graceful dance of winds to the whisper of falling snow, we have journeyed through the wonders of our atmosphere. Each phenomenon, once a profound mystery, has yielded its secrets to patient observation, ingenious experimentation, and the relentless pursuit of knowledge. We've learned that the atmosphere is not a chaotic entity, but a grand, interconnected system governed by elegant physical laws, a symphony of energy and matter. It is a system that provides the very breath of life, replenishing our waters, shaping our landscapes, and inspiring awe with its ceaseless transformations. The scientific journey into weather is a story of human curiosity, a testament to our innate drive to understand the world around us, from the smallest particle to the largest planetary force. And even with all our knowledge, the atmosphere retains a touch of mystery, a reminder of the vastness and complexity that still beckons exploration, urging us to keep looking up. It is a world of constant change, a delicate balance that supports all life, a system both powerful and fragile, deserving of our continued study and profound respect. So, as we bring our journey to a close, let the quiet complexity of our weather world settle within your thoughts, a soothing reminder of nature's artistry and the enduring human spirit of discovery. And so, as the moon climbs high, sleep well, knowing that the invisible dance above continues, a timeless symphony orchestrated by the very fabric of our world, forever inspiring wonder.